Hi everyone, welcome to part 3 of the video lectures on modern portfolio theory. In part 1 and part 2, we introduced the topic and we defined some equations that we're going to be using throughout the analysis that help us measure the return of our individual risky assets as well as the return of overall portfolio. We also went through an equation to help us measure the risk of our individual assets as well as the risk of our portfolio. And we introduced the concept of covariance amongst individual risky assets and how they behave in reaction to each other. And when we also went over the equation and the relationship between correlation and covariance. So today we're going to move on to the actual Markowitz mean variance optimization. But before we get to do an example on the mean variance optimization, we want to discuss how Markowitz's theory helped with the concept of portfolio diversification. So we hear this all the time that investors talk about diversifying their portfolio. But by this, an investor means that they want to construct a portfolio in such a way that the portfolio risk is reduced without having to sacrifice the return on the portfolio. Now, this is easier said than done. Achieving this in practice can be more difficult than just talking about it. And the more obvious question that comes into play is, and after that I have identified assets that have negative correlation and that move in opposite directions, how should I allocate my investment money amongst those assets so that my portfolio is the most efficient portfolio? So Markowitz's diversification strategy is primarily concerned with the degree of covariance between asset returns in a portfolio. And we can say that a key contribution of this theory is the actual formulation of the assets risk in terms of the portfolio of the assets rather than individual risky assets on their own. Prior to the development of this portfolio theory, investors often talked about diversification in general terms, but they did not possess the analytical tools to answer the above questions that you see on the slide here. So a major contribution of this portfolio selection theory is using the concepts that we have discussed so far and having a quantitative measure of diversification of the portfolio. And we're going to look at how we achieve this in real life by doing an example with a 2-asset portfolio first, and then we're going to move on to introducing more assets into our portfolio. Before we move on to our actual example, I want to introduce some of the key terms that we're going to be using a lot throughout. The first keyword that you should probably be familiar with is the definition of a feasible portfolio. Now, this is where you have to tap into your knowledge from linear programming and linear optimization that is taught in prescriptive analytics. A feasible set of solutions is any solution that is possible given the constraints or requirement of the particular problem at hand. So a feasible portfolio is any portfolio that an investor can construct given the assets available. This includes all the assets that you are willing and able to buy, as well as the total limit on your investment budget. So a collection of all these feasible portfolios can be referred to as the feasible set of portfolio. Diversification that Markowitz suggests leads to a construction of portfolios that have the highest expected return for any given level of risk. These portfolios are called efficient portfolios. Now keep in mind that an efficient portfolio is always a feasible portfolio, but not all feasible portfolios are efficient. So you can think of efficient portfolios as a subset of all feasible portfolios. So the efficient set of portfolios would be a subset of the feasible set of portfolios. With two assets in a portfolio, the feasible set of portfolio can be graphed as a curve, which represents the different combinations of risk and expected return that we can achieve by constructing a portfolio with different asset allocations. On this slide, we have an example of a two-asset portfolio. If you understand the logic behind a two-asset portfolio and diversification using two assets, you can expand that to three assets, four assets, five assets, and so on. So let's look at an example where we have two assets available to invest in, asset C and asset D. The expected return on asset C is 12%, whereas the expected return on asset D is 18%. And similarly, the standard deviation, which is a measure of the risk of the asset, is 30% for asset C and 40% on asset D. Now, if you ignore the returns and you just compare the standard deviations, we can say that asset D is riskier than asset C because of the higher standard deviation that you see. The return outcomes are much farther away from each other, so it seems like more of a gamble as compared to asset C. So over here in the table, the next table, what you see is 5 different portfolios that can be formed using these two assets by changing the proportion of allocation to each asset. So for example, if I have $100 to invest, I can either put all of it in asset C and nothing in asset D. That would be portfolio 1. Or I could form a portfolio where I invest 75% of my money, so $75 in asset C, and the remaining 25% in asset D. In the same way, by changing the allocations between C and D, we can create 5 portfolios here that we can decide to invest in either one of these 5, depending on which one comes out to be on top in terms of the performance of the portfolio. So if you look at the expected return of the portfolio, which you see here in column 4 of the second table, you'll see that when we change the asset allocations, the expected return also changes. This is because of the weights in the expected return formula. The weights are changing, which is why your expected return changes when you switch your money around between asset C and asset D. And the same way, the standard deviation, which is a measure of the risk of the portfolio, also changes. So if you have to draw these 5 different portfolios on a graph where the y-axis represents the expected returns and the x-axis represents the risk or the standard deviation of the portfolio, then you form sort of a curve-like figure here, which looks like a boomerang. So all I've done is I've plotted these risk-return combinations here on the graph, and when you connect the dots here, you sort of get a boomerang type curve. This curve can be used to help explain the concept of efficient portfolios and eventually an efficient frontier. In the case of the two assets, any risk-return combination not lying on this curve is not attainable, since there is no mix of C and D that will result in that risk-return combination. So these are the feasible set of portfolio that we can consider to invest in. Now, if we talk about a feasible set versus an efficient portfolio, if you look at portfolio 4 has a higher return as compared to portfolio 1, but it has that higher return at a lower risk level as compared to portfolio 1. So we can see that 4 is definitely superior to portfolio 1 because of the risk return trade-off. The same way, if you look at portfolio 3, it has a lower risk, but it has a higher return than both portfolio 2 and portfolio 1. And if you look at portfolio 5, although the risk is high, but the return is also the highest amongst all of the 5 portfolios that you see here. So what we can say is that the way we've defined an efficient portfolio so far is a portfolio. The efficient portfolio is a portfolio which gives you the higher expected rate of return with the same amount or lower amount of risk. So in that sense, this bold line, the bold part of the curve that you see here, would be the set of efficient portfolios that we can then select from, because 2 and 1 are both inefficient, although they are feasible, but they are not efficient. Therefore, for each level of risk, there is an efficient portfolio, or the whole collection of the portfolios together would be called the efficient set of portfolios. But depending on which level of risk you are comfortable with as an investor, you can decide which one of these efficient portfolios is optimal for you. Now, if we add more assets to our portfolio in addition to the 2 assets that we already had, the feasible set can now be visually demonstrated using what we see in the graph over here. This figure shows the feasible and efficient sets when there are more than 2 assets. In this case, the feasible set is not a line, but instead it's an area. So all of the area shaded here is a part of the feasible set of portfolios that we can invest in. This is because, unlike the 2 asset case, it is possible to create asset portfolios that result in risk return combinations that not only result in on a curve, but they're also in the shaded area here in the graph. It's easily seen that all the portfolios on the efficient set dominate the portfolios in the shaded region, because the efficient set is the set which is on the boundary of this shaded region. So the efficient set of portfolios is sometimes also called the efficient frontier, and a lot of the times when we talk about mean variance optimization, the first thing that comes up is the identification of the efficient frontier. So in this case, the efficient frontier would be the boundary of our feasible set over here, because those portfolios are the ones that basically outperform all the other portfolios in our feasible set. Now that we've learned how to identify the feasible set and the efficient set out of the feasible set, the question now arises: how do you select the most optimal portfolio for each investor once you've identified the efficient set of portfolios? And this is where we are going to tap into the basic concepts that we introduced earlier in the start of the topic about utility functions, and we're going to use those utility functions to help us select the most optimal portfolio for the investor that we are solving this problem for. Now that we've constructed the efficient set of portfolios, the next step is to determine the optimal portfolio. Since all portfolios in the efficient frontier provide the greatest possible return at their level of risk, an investor or an entity will want to hold one of the portfolios on the efficient frontier. Notice that the portfolios on the efficient frontier represent trade-offs in terms of risk and return. As we move from the left to right on the efficient frontier shown in the graph, the risk increases, but so does the expected return because it's sort of an upward sloping curve. The question then becomes, which one of those portfolios should an investor hold? The best portfolio to hold of all of those in the efficient frontier is called the optimal portfolio. Intuitively, the optimal portfolio should depend on the investor's preference over the different risk-return trade-offs. As explained earlier, this preference can be expressed in terms of a utility function. So let's take a look at how we use both utility functions and the efficient frontier to get our optimal portfolio. So if you recall, in the beginning of the chapter, we introduced the concept of indifference curves and utility functions. In this figure over here, you see three indifference curves representing a utility function as well as the efficient frontier drawn on the same diagram. An indifference curve indicates the combinations of risk and expected return that give the same level of utility, or in other words, happiness to the investor. Moreover, the farther the indifference curve is from the horizontal axis, the higher the utility. So utility 3 is higher than utility 1, and utility 2 is also higher than utility 1. From figure 4, it is possible to determine the optimal portfolio for the investor with the indifference curves shown here. Remember that the investor wants to get the highest indifference curve achievable given the efficient frontier. Because of that requirement, the optimal portfolio is represented by the point where an indifference curve is tangent to the efficient frontier. In figure 4, this is the point labeled as P star MEF, where MEF corresponds to the Markowitz efficient frontier. So this is a portfolio selected from the Markowitz efficient frontier, but because this intersects with the indifference curve U2, this is now our optimal portfolio for this particular investor. At this point in our discussion, a natural question is how to estimate an investor's utility function so that the indifference curves can be determined. Economists in the field of behavioral and experimental economics have conducted a vast amount of research in the area of utility functions. Though the assumption sounds reasonable that individuals should possess a function that maps the different preference choices that they have, research shows that it is not so straightforward to assign an individual with a specific utility function. This is because preferences may depend on circumstances and they may even change with time. Now, the inability to assign an investor with a specific utility function does not imply that the theory is irrelevant. Once the efficient frontier has been constructed, it is possible for the investor to subjectively evaluate the trade-offs for the different risk-return outcomes and even choose the efficient portfolio that is appropriate for the given investor's tolerance level for risk. So here, now that we have covered all the theoretical aspects of the Markowitz analysis, we can move on to an example where we will see how it can be applied for us to create a portfolio and decide on the optimal allocations for our portfolio. So I'm going to switch my screen to an Excel example that we're going to discuss and apply all of these concepts to that Excel example to help us get the optimal portfolio. Let's assume an example where we have to create a portfolio with 5 asset options to choose from. Now, you can create a portfolio with any combination of these 5 different stock options that are available to you. The first choice is stock 1, which has the returns, the historical returns for the previous 10 periods as given in column B over here. The second choice is stock 2, again with the historical returns for the previous 10 periods given in column C, and so on for stock 3, 4, and 5. So using these historical returns for these 5 different stocks that we have available, we can calculate their expected returns and their individual variances for each of the assets available here. So if you recall from the equations that we introduced in the modern portfolio theory discussion, in order to calculate the expected return of our portfolio, we have to decide what the optimal allocation has to be in each of these 5 options available to us. Also, in order to calculate the risk of our eventual portfolio, we have to know what the risk of the individual asset is. In addition to that, we also have to calculate the covariance, the pairwise covariance for each of these 5 stocks that are available. So in other words, we not only have to consider their individual variances, but also have to consider the covariances for each pairwise combination of the stocks. So for example, we have to consider the covariance of stock 1 with stock 2, the covariance of stock 1 with stock 3, the covariance of stock 1 with stock 4, and the covariance of stock 1 with stock 5. The same way we have to consider the covariance of stock 2 with stock 3, stock 2 with 4, and 2 with 5. Now, because we have 5 stocks available here and pairwise there are too many covariances to calculate, an easier way of solving for a situation like this would be to use matrices. So let's take a look at how we can use matrices to help us calculate the variances as well as the covariances and use them to get our optimal portfolio allocations. So on my screen now I've added a new table here, which is the variance covariance matrix. This variance covariance matrix is also sometimes referred to as the Hessian. And the way the variance covariance matrix is constructed is by placing each of the 5 asset options that we have in the form of a table. So you see stock 1, 2, all the way till 5 on the columns as well as on the rows. And the number that we're going to calculate in each of the cells in this table or in this matrix is going to either represent the variance of the stock or the covariance of the stock that we have on the columns and on the rows. So the first cell in our table is where we are going to calculate the variance of stock 1. In other words, this is the covariance of stock 1 with stock 1, which by definition is the variance. So by that rule, everything on the diagonal is going to represent the variance of that individual stock, and everything outside the diagonal would represent the covariances. So for stock 1, the first step would be to calculate the variance of stock 1. Now, assuming that these 5 stocks are the only choices that we have for investment, we can assume that this is the full population that we're working with. So I'm going to use the population formula for variance. Variance dot P, and here I'll select all of the 10 holding period returns that we have for the previous periods, and close the brackets, press enter. This is going to give you the variance for stock 1. Next is the cell in the same column, in the same row, but the adjacent column is where you're going to calculate the covariance of stock 1 with stock 2. So again, we're going to use the covariance formula, and I'll use the covariance dot P. Here, remember that you need to have two sets of cells or two arrays as inputs so that you can calculate the covariance between those two stocks or the two assets that we are considering. So the first array would be for stock 1, because this is a covariance between stock 1 and stock 2. And the second array would be the returns for stock 2. And that's going to give you the covariance between stock 1 and stock 2. Notice that the covariance is positive, which means that when stock 1 goes up, stock 2 is also going to go up. But because it's not a perfect positive relationship, it's not going to be a one-on-one increase. Then moving on to the next cell, this is where we calculate the covariance of stock 1 with stock 3. Again, I'm going to use the covariance formula, and the input arguments would now be the returns for stock 1 in combination with the returns for stock 3. So now you get the logic. We can apply the same formula to the remaining cells in the same row. Notice that the returns for stock 1 remain constant because this whole row represents stock 1, and the column represents the second asset that we are comparing this to. In this case, that's stock 4. And press enter. And similarly for stock 5, it would be the covariance between stock 1 and stock 5. So that gives you the full row and the variance and covariance of stock 1 with itself, as well as the covariances with the remaining 4 choices that we have available for our portfolio selection. Moving on to filling out the row with stock 2, you're going to use the same logic. So the first cell would be the covariance between stock 2 and stock 1. So you're going to use the covariance formula again with the returns of stock 1 and stock 2. Now notice that this number is the same as what you calculated in column 2 of row 1. And this is going to be true for all the values below as well. The reason for that is that the Hessian matrix, the diagonal represents the variances of the individual stocks, whereas the upper triangle is going to be a mirror image of the lower triangle below the diagonal, because in covariance the order does not matter. The covariance of stock 1 with stock 2 is the same as the covariance of stock 2 with stock 1, so you will see these numbers repeating on the remaining cells as well. Moving on to the next column in the same row, this is the covariance for stock 2 with stock 2. So the covariance of stock 2 with itself will simply just be the variance of stock 2, and you don't need two arguments here, and that's going to give you the variance of stock 2. The same way you're going to calculate the covariance of stock 2 with stock 3, and so on. So I fast forwarded and I filled out my variance covariance matrix with all the formulas. The formulas that I've used to fill out this variance covariance matrix is the var.p, which calculates the population variance, and the covariance.p, which calculates the population covariances between pairwise combinations of the assets here. So if you click on the cells here, you'll see that the formula that has been used to calculate these numbers here. So now we have an idea of what the individual risk of each stock looks like, as well as how they move with respect to each other. Now we have enough information for us to be able to start our process for calculating optimal allocations in our portfolio. After calculating the variance covariance matrix numbers in here, we are ready to calculate the expected return for each of the individual 5 risky stocks that we are considering to be a part of our portfolio. So I've created here a little template where I'm going to add the expected return for each stock in this row 25, and above that row I have created a row where I'm going to store the weights of each stock in my portfolio, and I have to make sure that the sum of these weights equals to 100%. So let's put that sum formula in here just to make sure that whatever allocations we come up with do not cross 100%. So right now it's 0% because these cells are blank, but once solver gives us the solution, this is going to be populated with the optimal weights that we need to assign for our efficient portfolio. And right underneath these weights, I'll calculate the expected return of each of the individual stocks listed here. The expected returns are, if you're assuming a probability distribution on your risky assets return, then you would use those probabilities to get the expected return. But here we're using historical values to get the expected returns. So the expected returns in this case would simply be the average of these historical returns. Oops. So just the average formula here. And I can drag this across to get the expected return for all of the 5 stocks. Recall that in order to calculate the variance of your portfolio, you have to add the individual variances of the stocks or the shares themselves and add the covariances of the stocks with each other as a product of the weight that they have in the overall portfolio. So to calculate our portfolio variance, the formula can be a bit confusing in Excel, but we're going to use the same logic that we saw in the equation for calculating the portfolio variance here as well. So the cells that we're going to need in order to calculate the portfolio reference, the portfolio variance is given here. So our full variance covariance matrix. Now I'm going to note down the dimensions of this matrix here, and I'll get to why this is important. If you remember from our previous classes, matrix multiplication is not the same as regular multiplication. The reason for that is you have to match the number of rows and columns when you're trying to multiply 2 matrices together. So for that, we need the dimensions, and we need to consider if there are any transformations that we need to do before we are able to multiply 2 matrices together. The 2 matrices that I'm referring to right now for here is the first is the variance covariance matrix here, and the second is the matrix or the row matrix of the weights for each of the stocks. Although these are empty for now, but when we move to solver, these will be populated, and the formula that we put in here, Excel will use that to populate these cells in yellow. So let's put down the dimensions of our first matrix. The first matrix, which is a variance covariance matrix, is a 5 by 5 matrix. So that means there are 5 rows here and 5 columns respectively. The dimensions, let's call this M1 for now. The dimensions of our second matrix, let's call this M2, is 1 by 5. Because the second matrix that we're going to consider for calculating the portfolio variance is this row matrix of the weights of each of these 5 stocks. So it's 1 row and 5 columns here. So here, in order to calculate the portfolio variance, we have to multiply the weights that are given in the set of cells labeled in yellow along with the variance covariance matrix here. So to do that, I'm going to use a special function in Excel, which is used for matrix multiplication. Remember when we were doing this in R, there was a special symbol for matrix multiplication. The same way in Excel, for matrix multiplication, there is a special function called mmult. And when you start typing it, it gives you the option mmult, which returns the matrix product of 2 arrays, an array with the same number of rows as array 1 and columns as array 2. Okay, so I'll type in the mmult function in here. Now keep in mind that the mmult function only works correctly if you don't press enter after completing the formula right away. Instead, you press Control, Shift, and Enter, all 3 buttons together. Otherwise, you're going to get a value error. So when we get to that part, don't press enter right away. Instead, press Control, Shift, and Enter at the same time. And that's the only way mmult is going to give you a solution. So the formula that we're going to use, I've also typed out all formulas that I'm using on the right side on the screen here, so that you can always refer back to these in case you miss out during one of the steps. So the first array that we need to fill into our mmult function is the multiplication of the variance covariance matrix with the weights, optimal weights matrix here. So the first array that will go into my mmult array would be the row of the weights that I have. So I'll put the cell reference here of the rows. The next function would be the variance covariance matrix, which is up top here. Okay, now the formula is not complete yet, because if you refer back to the original formula that was given in the PowerPoint presentation for calculating portfolio variance, we have to multiply the weights twice, because all of the weights are either squared up, or for the covariances you have to multiply the weight of each of the pairwise stocks in your model formulation. So this means that I have to multiply this matrix that I just put in the formula for again one more time with the weights. The reason is for the quadratic nature of the weights variable in our formula that we saw earlier. So here I'm going to use another mmult function. And this mmult function will sort of nest the earlier mmult function that we had put in earlier. And if you recall from matrix multiplication, if you're multiplying a 1 by 5 matrix with a 5 by 5 matrix, it results in a 1 by 5 matrix. So in order to get the dimensions correct for this multiplication, I have to transpose my weights matrix from a 1 by 5 matrix to a 5 by 1 matrix so that I'm able to multiply that with the product of this original mmult function. So here I'm going to use the transpose function within the mmult function, and the transpose would be the transpose of B24 to F24. Now notice that after I have finished typing down my formula the way I had intended to, I have not yet pressed enter, and this is where you have to be careful. You have to press enter along with control and shift pressed on your keyboards. Oops. Now, even though we followed the procedure correctly, you will notice that we are getting an error here. The reason for that is because the weights are actually not filled in, so Excel is automatically thinking that these weights are equal to 0, which is why you get this error. So just to make sure that our formula has been added correctly, I'll put some hypothetical weights in here just to make sure that our function for the portfolio variance is working just fine. Yep. So when I put numbers in the matrix for the weights, you get a correct value here. But because these were set to 0, because we don't know these optimal allocations yet, you might see a value error in here. But as long as you've added the formula correctly and you pressed Control Shift Enter before leaving this cell, you should be good. So even if you are getting a value error, I would suggest that you can go back and put in numbers into the yellow cells and then check to make sure that the function is working correctly. Again, because my cursor is in the cell right now where I have the mmult function, every time I leave this cell, I have to press Control Shift Enter so that the matrix multiplication is working correctly. And one hint for you that tells you you've used the matrix multiplication formula correctly is when your cursor is not on that cell, but you can still see the formula for that cell, you'd be able to see these curly brackets around the function. We did not add these curly brackets. Excel automatically adds these curly brackets when you press Control Shift Enter for any sort of matrix operation to get the correct answer. So now we have a value in there for portfolio variance. I'll keep these numbers in there because Solver is just going to replace them once I run it. So this serves as the objective function of my optimization model, and I need to minimize this. And I'll put that in front of it so that when I get to the solver window, I know and I remember that I should select the minimize option, because portfolio variance measures portfolio risk, which we want to keep at the minimum possible level in order to achieve our optimal allocations. Although we are using variance in our overall model, but it's a good idea to have the standard deviation in there as well, just so that we know it. So we'll calculate the standard deviation as well, which is the square root of the variance. And now we have to populate the cell for portfolio return. The portfolio return would just be the sum product of the portfolio weights with the expected return of each of the stocks in our portfolio. So I'll put the sum product function in there. And our hypothetical portfolio right now has a portfolio variance of 0.21% and a portfolio return of 9.34%. So now we have created our Excel template and it is ready to be put into Solver. I just added a little explanation here in case it's easier to read as to why we had to use the mmult function and why we had to use the transpose function within the mmult function. So in case my verbal explanation was not clear, I've added some text over here which you could read in case you're still confused about that particular formula. And the formulas that I've used are also added here on the screen so that if you're practicing on your own, you should be able to follow along. So now we are ready for us to be able to use Solver to run this model formulation into and get the optimal allocations for our optimal portfolio. So in order to access Solver, you have to go to the Data tab in your ribbon on Excel, and at the very end up top you're going to see the Solver analysis tool that we're going to use. If you do not see Solver in here under your Data tab, please follow the instructions to install Solver. I will be making them available on Canvas. So press Solver here. So this gives us the Solver window that we need to populate. You have to first set the objective, which would be this green cell here. If you recall, I always use a green cell to identify the cell that I'm using as the objective function for my model. And in this case, it's the variance because our objective is to minimize the risk of the portfolio. Again, I'll set that to a minimum. The changing variables are the variables where your decision variables go. So this, I've added the yellow cells highlighted here because this is where the solution is going to be populated. This is where Solver needs to put in the optimal allocations. So I've added the cell references for the decision variables, which are our weights, into the Solver window. Notice that initially we had set it to 0, but even if you leave values in there, Solver will just overwrite over those values, so you don't have to worry about that. Then we have to add the constraints to our model. Sorry, my Solver window was already populated. Let me just delete these constraints so that I can add them with you together. Okay, so now that my Solver window is empty, I'm going to add the constraints one by one. The first requirement of my model is that the sum of these weights should not go beyond 100%. So I'm going to add that constraint as this sum, the total, where I've added the sum function already, has to be equal to the value that I've assigned here as 1. You don't have to put this cell in here. You can put 1 automatically in there as well and get rid of this cell reference, but just in case you don't open the Solver window, the next time you open this workbook, you can see that what this has been set to. So set that equal to 1. Press OK. That adds the first constraint that we added to our model. The next constraint is that all of these cells need to be greater than 0. So I'll add that constraint that all of the weights in my model have to be greater than or equal to 0. So I'll put 0 manually in there. So far I've added 2 restrictions on my model. However, if you recall from the PowerPoint presentation, we said earlier that in order to get the optimal allocation, we need to know what the preferences of the individual investor are going to be. So because we are limited with the scope of this topic for the purpose of this class. We don't want to get into utility functions and go over the whole chapter on indifference curves and calculating utility functions. An easier way to set the preferences of the investor would be to set a minimum on the return that the investor is expecting from the portfolio. That way, we're incorporating the preferences of the investor into the model to get the optimal allocation. So let me close the solver window for a second. I will come back to this after we have set our preferences. So let's say that our investor wants at least a certain amount of return on their stock. And if you look at the individual expected returns of the stocks, the lowest return is for stock 5, which is about 6.9%, and the highest return is for stock 4, which is about 10.7%. So our portfolio should be able to get us a return which is at least as good as the return on investing only in stock 5. So let's say that the investor wants to have a minimum return of at least 7%. Let's go with 7% for here. So let's say that the investor wants at least a return of 7%, and the allocations should be assigned in such a way that the risk of the portfolio is minimized, but we should be getting at least 7% return on our investment. So now I'm going to open up my solver window again. Go to Data, Solver. The good thing about Solver is that it does not erase the contents when you close the window, so you can continue from where you left off. So here I'm going to add this as an additional constraint, that my overall portfolio return needs to be greater than or equal to this return of 7%. Again, you can type the 7% manually in here, or you can put the cell reference and put the 7% in your Excel workbook. Now our model is complete. Make sure that you have selected the Make Unconstrained Variables non-negative checked, and you have to select a solving method. Normally, if we're solving a linear programming problem, we use the simplex method, but because of the variance formula contains the quadratic function, we're going to use the GRG nonlinear algorithm to help us get the solution, and hit solve. Solver has a solution for us. Press OK, and we get our optimal portfolio allocations, which looks like we should be investing 54% of our money in stock 3 and 46% in stock 5. That way we get the minimum portfolio variance of 0.02%, sorry, and a portfolio return of 8.25%, which is much higher than the limit that we had set for ourselves at 7%. So although if you look at the solution, it might look a little bizarre because stock 4, which was the highest expected return, Solver is telling you not to invest in there. The reason for that is probably stock 4 has a positive correlation with all the other stocks in our portfolio that we are considering, whereas stock 5 has a negative correlation with 2 of the stocks, which is why the optimal allocation is telling us that we should be putting our money into a combination of stock 3 and stock 5 in such a way that we get the minimum portfolio variance, which is much smaller than the individual stock variances, and we get a higher expected return, which is higher than at least 2 of the stocks that were available to us. So this way we learned how to create an optimal allocation model in Excel using 5 assets as options for our portfolio.